In this segment, we'll delve a little more into Bra and Ket vectors that we'll look at this juncture. And just to recall, Dirac found it useful to think of the wave function as being the component of a time-dependent vector in a certain sense, where x labels the components of the vector, and so it uses this as called a Ket vector. We introduced that last time. And it's like the components vi of, say, the velocity vector. Vi, velocity is a function of time, right here. For a finite number of components, you occasionally have quantum systems that only have two states. And so you might very well just have a wave function psi that has only two components here. And they're very much analogous to complex vectors. But for any complex vector, you might remember that you can form what I call V dagger here. And that's simply the complex conjugate transposed. And for us, if I've got V1, V2, V3, then V dagger, that's sometimes called the Hermitian conjugate, is the row vector in which each one of the components is just the complex conjugate of the components of the column vector. We can do the same thing analogously for any Ket vector. We can form a vector called the Bra vector, which is effectively the Hermitian conjugate or the transpose of the complex conjugate. And it'll be a bracket that looks like this. So these are the Ket vectors. These are the Bra vectors. Psi is equal to the complex or the Hermitian conjugate. Again, this is a dagger, which is just this thing, complex conjugated all of its components, and then taking the transpose of it. So, for example, if we've got a finite dimensional quantum space, things like this occur, spin up and spin down, for instance, then this might be the Ket vector representation of psi. And I can take the complex conjugate and then transpose it to get the row representation of the same vector. Notice there's not any more information in the Ket representation as there is in the Bra representation. It's just two ways in deciding whether you want to do a column matrix or a row matrix. Note also that I can form between a Bra and a Ket representation, I can form with these two this product between the two. It's really an inner product. I have the Ket representation here. I'm sorry, the Bra representation here, the Ket representation here, and then I just use regular matrix multiplication to multiply that out. And in this particular case, if you do that, you find that it's equal to 1. So this is a properly normalized Bra-Ket representation of a quantum state, quantum system. And the thing for us is that it's very, very much like a scalar product. So this notation leads us into an analogy for a scalar product between a complex vector. A complex vector is just the sum over all of its components that take the complex conjugate of the first one and multiply it times the corresponding component of the second one. For two quantum states, say I've got these two states, then I can do a similar kind of thing here. I simply take the complex conjugate of this one, psi star. Remember, x is labeling the components and t is the time dependence. And multiply that times the corresponding component, psi x and t, again x is labeling, and then sum that over all the components like you do in the case of the usual dot product. Note that in this representation, if you look at it, in general, you where the terminology comes from. This was the Ket vector, this was the Bra vector, and you put them together in this inner product between them. It forms a number, a numerical value, and so it forms a bracket. We bracketed these two, and so the Bra part comes from the first three letters of bracket, and the Ket part comes from the last three letters. So some notation for Bra and Ket vectors.